Okay, we are starting lecture number 7, and this lecture will be about positive definite matrices. This is again part of the review, but probably many students have not seen the positive definite matrices definition before. So this can be brand new for some students. So let's start with our simplest case. So what is the simplest case? Assume that we have a quadratic with one independent variable. For example, let's see. I have x squared minus 4x plus 9. Okay. So we know lots of things about quadratics, especially for one variables. And in this lecture, we will extend this knowledge to multiple variables. And on that way of extension, we will also define this positive definite matrices. Okay, so when we see a quadratic, so what we think about it? So since from high school or maybe from secondary school and so on, what are the issues? This can be what we say concave up, or it can be concave down. It may have two roots, or it may have a single root, but a repeated root, and so on. This has no roots, and so on. So how do we think about those things? Important thing is these coefficients. So this coefficient is 1. We call this A in general. This is minus 4. This is this. And C is this. So we have the definition of discriminant. B squared minus 4AC. Please remember, we have discussed that before. To understand whether we have repeated roots, we have no real roots, etc. So how do we decide on, well, this is concave up or concave down? We just check the sign of this A. So remember, sign of A, immediately A coefficient immediately gives away whether quadratic is, let's say this way, concave up, or let's say down, concave down. I don't actually remember these definitions, how we describe them very well, concave up, concave down, but I think the picture is clear. Okay, what else? So let me try to find from calculus. Let's find extrema or extremas, if there are multiple of them, or extremum. Okay, extremum is the plural one, and extrema is the singular one and the plural one. So how can we find what is the meaning of extrema? So this means it's the extremum point. So this means minimum or maximum. Well, very easy. Now from our basic calculus knowledge, we know that if I take the derivative of jx, which is this thing, 2x minus 4, and equate it to 0, now I have the information that x is equal to 2, is the point where the derivative is equal to 0. So this is right now an extremum. Okay. Now I don't know whether this is minimum or maximum. So for quadratics, because I know that this is, for example, a is greater than 0, this is concave up, I can immediately say that this is indeed a minimum. So how do we check this? Well, in general, you check this by second derivative, and let me call this special point OPT, optimal point, let's say. You check the derivative at the optimal point, this point. If I calculate the second derivative of this, I get 2. Okay? which is 2 times a. Since this is greater than 0, then we say that this is x's corresponds to a minima. Okay? So what I know right now is, if I sketch this, at x is equal to 2, this is j of x. Okay. This j of x is taking the value of 4, minus 8, minus 4, plus 5. It takes the value of plus 5. So it takes this value, and my general knowledge is, of course, I know how it, something like this. Okay. Okay, very good. Now, let me also define one more thing. In general, we don't do this because it's a very simple problem. So let me define a u variable over here, u. Or u can be defined in the other way also, depending on the case. Okay. So let me define u as x minus 2. Okay. So u is, you may consider, u is the deviation or distance from, in our case, x opt is equal to 2. So when our distance or deviation from, when x is equal to 3, let's say, then this u is equal to 1. So we are 1 unit away from this x opt point. So let me also try to do the following. Now, if I define, for example, another function, ju of u, okay. So how can I define this? So this is j. Let me think about this. X minus 2, okay. So this is our, so I will call this u later on. X is equal to u. So j is equal to this function. Now, as you can imagine, I am trying to move this optimal point to the origin. So by this shift, I'm moving this optimal point to the origin. And right now, after this operation, translation operation to the optimal point to the origin, I'm calling this new coordinate system with u, let's say. Okay. So I can define a new function. So j of x is this. So I should do x minus 2 square minus 4, x minus 2 plus 9, something like that. But if I do this, well, let me erase this part. There is a minor mistake. So if I do this, then u is equal to x minus 2, then x is equal to u plus 2. So I should write this, let me call this in terms of x. Okay. jx u plus 2. Okay. That is it. So instead of x, I am writing u plus 2, because at the end I want a function of u. That is the thing that I have realized at the end. So I need a function of u. Okay. So I have u plus 2 square minus 4 u plus 2 plus 9. Okay. So if you check this, I have u plus 2 square u plus 2 minus 4 plus 9. Okay, so what do I have? I have something like this. I have u squared plus, this is u squared minus 4 plus 9. So I have u squared plus 5. Okay, this is 5. So I get this deviation function, u squared plus 5. Okay. So what do I get from here? Now, if I'm at this point, if u is equal to 0, if deviation is equal to 0, I get, if u is equal to, I get the value of 5. This is what I know actually. So if deviation is 1 unit away, you see that it's always positive. So I get if this is deviation factor is 1, then I have 1 squared plus 5, the total is 6. But what I know is that from here, since u squared is always positive or greater than or equal to 0, then u is equal to 0. So when the deviation is equal to 0 is indeed the minimum of ju. So when I'm deviating by 0 units, I get the value of 5, and if deviation is non-zero, as you see over here, then you get higher values. Of course, we don't do this for the quadratics because this is such a simple, we know lots of things about quadratics. But in general, if you don't know anything about the function, you check what happens around this optimal point, okay? You find this optimal point by derivatives and so on. There is a second derivative check, but this is more elementary. Without the second derivative check, you are trying to understand what is going on around this. This can be local optima or a global optimal. We don't know anything about that, but this is the way you check this, okay? So you define a deviation factor u, then you express this function in terms of deviation factor, and you analyze that function. Okay, that is it. This is, again, almost like high school kind of mathematics, isn't it? Now, let me try to do the following. Let me define, this time, the following. Jxy. A function of two variables. X squared, y squared, 4xy, plus 2x, 5y, plus 1. Okay. Now, this is a little different because I have two independent variables, as you see. Okay. So what is the simplest case of this? Well, simplest cases, actually, this is J circle, let me say. X squared plus y squared is equal to, let's say, 100. Okay? So, what's the meaning of this? If I sketch this, now I have, or let me erase this 100. Okay? So this is the locus of points, let's say. X squared plus 100, 10, 10, minus 10, minus 10, and it's a circle, as you can imagine. So what do I mean by this? Now, I am sketching this function, and this is the locus of the points for which this function, which we call this cos function, okay, later on. This cos function takes the value of 100, okay? So this is a circle. Of course, if this is, let's say, 16, I have another circle like that with radius, let's say, 4, okay? This is the case when the cos function is taking the value of 16, okay? Something like that. So we know this from very well from earlier courses. This is the equation of a circle and so on. So, but this interpretation is very important for us, and these are called the level curves. Level curves for this function. Level curve means the following. You are assuming that for every xy point, this function takes the value. For example, when x is equal to 10, y is equal to 0, for this xy point, the z, the height above this plane, let's assume that that is the value of this function, then it becomes 10 squared plus 0 squared, it's like 100. So it takes the value of 100 and it becomes something like that. So if you cut this at this 100 slice, you see that this is also on that slice, on that slice, on that slice, and so on, so I get a circle. So if you consider this function is something like what we call, it's like concentric circles. It's like a ball-shaped function, okay? So in 3 dimensions, so this function is from this point starting and it's increasing like that, okay? Above this plane, it's going towards in the z direction, it's increasing like this. So when I cut that function at a specific z point, let's say z is equal to 100. So z is this. Now I'm taking the value of the function and evaluating at the z point. When z is equal to 100, I get this curve. Okay, this is called the level curve. So the slice for which this function takes the value of, let's say, 100 and level curve. Now the question is, what can I say about such a function? Okay, this is more complicated, but what can I say about it? Is it, for example, what are the level curves of that function? Is it a circle, ellipse, or is it something else, and so on? Okay, so we have such a case. But before that, let me try to find the optimal points for this. So this time you are taking, okay, derivative with respect to, partial derivatives with respect to x. Okay, partial derivative with respect to y. And equate these partial derivatives to 0. Okay. Then you say that by solving this 2 by 2 equation system, x is equal to 4 over 3, y is equal to, minus 4 over 3, this is 1 over 6, and that is the result. Okay. That is the solution of this equation system. Now the question is whether this corresponds, this point, optimal point, let's say. So I'm on this xy plane. X is minus 4 over 3, y is 1 over 6. This function, if you evaluate this function, it takes a value over here. Now, so is this function, if I go, for example, this way, or that way, or go up in the diagonal direction, do you think this function is increasing or decreasing? Okay. So is this point corresponds to a maxima or minima? So for the simple one-dimensional quadratic case, we had an easy check, second derivative check. So for this one, what can we do? So what we are going to do is, we will generalize this earlier result to multiple dimensions, so for multiple variables. So to do that, so what we need is, now I will write this x vector with some abuse of notation. Now my x vector is x and y, okay? So I will write this as x transpose ax plus x transpose b plus c. C is just a scalar. Okay, these are of course vectors, this is a matrix, and so on. So what's the meaning of this? By the way, we will call this quadratic form. Okay? So this is very general. If x is not a vector but a one by one vector, let's say it's a scalar, then we have this earlier case. This capital A with double bar becomes of course a scalar. This becomes a scalar, everything becomes a scalar. We have the usual case. But in multiple dimensions, not only 2, it can be 50 dimensions, this equation will be called quadratic form. Okay? Now, let me write this explicitly, xy. So I need a matrix with some entries. Now I have xy, a vector like that. This will be my b vector. And c, I need a number over here. Now the question is, if I define this vector valued function, so how can I equate this vector valued function to this function? But I think this part is easy. I think this will be 1. How do I set that? Because when all of this is equal to 0, I am getting 1. Well, I think it's obvious this should be equal to 1. Then I have coefficient of x is 2, coefficient of y is 5. 2, 5. That was also good. Now coefficient of x squared is equal to 1. So how can I understand? This is the critical part. Maybe this is a little bit new. So if you do this multiplication, So if I have A11, A12, A21, A22, if I have such a multiplication, again a quadratic form, okay? Without this linear term and the constant term, of course. This is a quadratic form. So what's going on? So at the end, I get a scalar, isn't it? So I get a scalar quantity. So this is not a vector. This is not a matrix. Obviously, this is a scalar quantity. So now the question is, what is the coefficient of A11 in this scalar quantity? So coefficient of A11, this coefficient. So you see that this multiplication occurs like this. I can first multiply, maybe this part. You see that A11 is multiplied by, first row, first column. A11 is multiplied by x. So let me write x over here, y over here. Because if you check this, xy multiplies this, xy multiplies this. That is it. Okay. So you see that second row is multiplied by y, first row is multiplied by x somehow. Now if you forget about this, now if you check this part, you see that A11 from the other side, it's also multiplied by y. Because as we have discussed before, this coefficient scales first row, first column, the other coefficient scales the second column. Similarly, from this side, this coefficient scales first row, this coefficient scales second row. So what I see is the following. Now this A11 is, if I do this multiplication, if I put this bracket over here, multiplied by x, then that result will be multiplied one more time by x. So I see the following. A11 is multiplied by x square, A22 is multiplied by y square, and so on. Okay. So once I get that, and I paid attention to this, so it's as if you are multiplying individual terms by these xy pairs and summing them up. Okay, that is what we do. Now given that knowledge, now this is x squared, coefficient has 1. Well, I see this is equal to 1 then. Y squared, coefficient is equal to 1. I have one more 1. Then xy is equal to 4. Well, xy, this is equal to 4. Maybe, well, I can have 4 over here and 0 over there. Because this will be giving me x squared plus y squared plus 4xy, 0yx. Okay? Because their addition will be a21xy, a12xy will be forming this 4xy. I can have something like that. So as you see, I have some freedom in the selection of this. So in general, we make this matrix symmetric. So we have 2, 2. Okay? So the case is, I have 2xy plus 2xy, making 4xy, and that will be it. So why do we prefer symmetric matrices? Well, symmetric matrices have, as we have discussed before, orthogonal eigenvectors. That is the reason symmetric matrices have some nice features. Orthogonal eigenvectors, real valued eigenvalues, and so on. So they have some nice features that we can use. So this is the reason. Why not use a symmetric matrix if I have a choice? Okay. That is the case. Now, what else? Now, I should do the following next. Now, if I have Jx in this form, x transpose Ax, this is x transpose B plus C. Now, I would like to define the gradient operation. Gradient with respect to this x variable. Okay? So what is that gradient operation? Actually nothing different. It is the partial derivative of this j with respect to x and partial derivative with respect to y. Because x vector contains x and y, so this is gradient is partial derivatives. This is the definition of the gradient. Partial derivatives with respect to the independent variables. So how can I calculate this? Of course, I want to use these ABCs. I don't want to solve this specific problem, so I want to have a result, something like that. So let me write the answer and then let's discuss. So what's going on? Now, let's go back to this. Let's say that I'm taking derivatives with respect to x. So what's going on? Let's check this part. So I operate with partial derivative with respect to x. So if you calculate this, you have 2x, 5y. If you take the derivative with respect to x, essentially you are taking the derivative of this. You have 1 and 0 over here, so you get 2. If you take the derivative with respect to y only for this one, because this is 5y, you get this 5. I think that explains what's going on over here. So if you have a linear combination of x vector entries and linear coefficients are b, if you take the partial derivative with respect to x, you get 2, partial derivative with respect to y, you get 5, so this is b vector itself. So how about this one? This is the quadratic term. Again, if this is a scalar, like 1 by 1 matrices, so we know that this will be 2a, 2 small a, because it's a quadratic, 2a. So we get something like that, a plus but a transpose. You should be a little bit careful. So again, let's go back to this. Now, I know how this thing works. So x transpose ax, in terms of this interpretation, I know how it works. So if I take derivative with respect to x, for example, this entry, a22, won't be having any, because a22 is multiplied by y square, okay? So if you take derivative with respect to x, what's going on? So first column and first row entries will be affected, because x is multiplying, as we have discussed, either first column and the first row entries, okay? So if you do that, for example, let's think, if I take derivative of this quantity with respect to x, this term it will be 2a1, okay. This will be a1 2 times y, if I take the derivative with respect to x, okay. This will be equal to, again, a2 1 times y. So what do I see? I see the first column and first row of this matrix added up, okay? Well, if I explain this a little better maybe, if I calculate this part, so what do I get? 2a11 plus a12y plus what is this one? a21 y and the other entry. So I get 2a22 a12x a21x, okay? I get something like that, plus this is our b vector, generic b vector, and so on. So what's going on? Well, you can see in this case I have according to this, it has to be something like that. So this is the transpose of this A matrix. These entries are exchanged. And this should be this result. So is it indeed the case? Oh, let's check this. I have 2a1 times this. a1, a2 times here. So a1, a2 times this. So what's going on? The thing is, when you calculate this term, well, because of this x squared, it comes into the play with the factor of 2. But the other terms, this one and this one, all of the other terms, if this is not a 2 by 2 matrix, but let's assume that this first row is very long. So except this 1 entry, all of these other entries will be multiplied by this y. The third entry will be multiplied by z, fifth entry will be multiplied by something else, and it will be copied down. Okay. Then similarly, the other ones, they will be multiplied by y, so on, so on, so on, and it will be multiplied by 1. So that is actually what is going on. All of these entries this one. This can be longer. They are multiplied by this other entries over here, and that is it. So this becomes first row. This becomes after transpose. These are the first column entries, as you see. Okay. So my comment is, well, this is the gradient result. I have tried to explain this a little bit. Okay. So this is the result that we will use. So if we, of course, apply this, we get this matrix. Since it's already symmetric, I have 2, 4, 4, 2, xy plus 2, 5. Okay. Actually, now I'm at this point. 2, 4, 2, 4, 2, 5. 2, 4, 2, 4, 2, 5. Okay. I have that. Okay. So this is the same equation system. Now, if I equate this, gradient is equal to 0. That is what we do. Not only in 2 dimensions, but in 50 dimensions and so on. Just A matrix will be bigger. B vector will be longer. Then we get this optimal point as before, minus 4 over 3 and 1 over 6. Okay. So if I check this equation is A transpose X optimal is equal to minus B. Okay. So this equation is, well, obviously, because of this equality, I have this. Now the question is, earlier question, is this corresponds to a maxima or minima? Okay, so what can I say about that? So let me erase this part. So let me call this XOPT vector, compatible with this. So these are the coordinates of this XOPT. So without the bar, they are scalar. With bar, it's a vector. So I will do a similar thing. Now let me assume an X vector, sorry, U vector. This is X minus XOPT. Do you remember for one-dimensional case, we have done something like that? So again, I'm trying to shift this XOPT point to the origin. Okay. That is, what am I going to do? So this is the definition. I have something like this. So let me write J UU as we have done before. Then J, this is X. This is again the definition of JU. Okay. X, what is U? U is equal to, sorry, what is X for this one? U plus XOPT. Okay. XOPT is this constant vector. I have calculated its values and so on. Then let me do this. U plus XOPT transpose. There is A matrix. U plus XOPT plus I have X transpose. U plus XOPT, let me put transpose over here. Transpose and transpose. Oh, it's not very visible. B plus C. Okay. I have something like that. So let me try to expand this. So my purpose is understanding what is going on around that point. Okay. So I have 4 terms over here. So I'm writing other term. I have XOPT transpose A XOPT. What else? So right now, 1, 2, 3, 4, all of these terms corresponds to this one. Plus, so let me write these two. U transpose B plus XOPT transpose B plus C. So this second one corresponds to this. So I get that. So 4 terms, 7 terms, or 6, 7. Okay. At least number of the terms matches. Okay. So what do I have? So one thing is, obviously this is a scalar. Scalar means 1 by 1 matrix. Okay. Because this is a row operation, this is a column operation. At the end, you get a scalar. This is also a scalar, because it's in the same form. Actually, all of them should be a scalar, because this corresponds to, at the end, addition of scalars. And this is a function. At the end, you get a real number. Remember, this function is x squared plus y squared, 4xy, and so on. So we are adding scalars. Each of these terms is scalar. So how about this? Now, if I take transpose of this, let me write it over here. Since this is 1 by 1, this is a scalar, it transposes itself. So XOPT transpose A transpose, because it's just a number. Maybe this is 5, this is 6, I don't know. 6 transpose is 6 also. Okay, that is it. So this is equal to this. Now if I combine these two, then one more step. I get something like that. Because left and the right vectors are common right now, so I can collect them together. I get a result like that. So how about this? This and this. Okay. Now, since this is an optimal vector, or let me take transpose of this one more time, if you wish. This is U transpose. XOPT. Now I have this result. Because this is the optimal point, AA transpose, this is supposed to equal to minus B. Okay. Because this is not an arbitrary, XOPT is not an arbitrary point, but it is this point. And this point satisfies this equation. And I have this minus B over here. So this is also equal to then U transpose minus B. Okay. And that's my comment actually. U transpose minus B. So I have cancellation of this term, which is, these two, with this. Okay. So at the end, I get the following. U transpose AU plus, I have XOPT A XOPT plus XOPT B plus C. C is constant. That is it. So what is this? This is my deviation function, as I have said. This is my JU of U. And you can say that this is indeed the value of this original function, XOPT. So this is J with respect to X, let's say. Now I have two J's. So for the optimal value, this function, quadratic function, takes this value for the optimal vector. Okay? So, like in the one-dimensional case, so this is just a number plus, now you see, in the one-dimensional case, I get like U square over here, that A was 1. So we get a very similar result. Okay. So if I can guarantee that, for example, this matrix is, this quadratic form is always positive, this is always positive for any U, Like in one-dimensional case, it was like u square, isn't it? It's always positive. Now, if I can guarantee that this is always a positive quantity, now this is indeed a minimum. So I should study this. So how do you study that? So let me write a definition. Positive, definite matrices. Now you see the application of this immediately, isn't it? A matrix U, number 1, if X transpose, let me say A because let's make it for general, more generic, greater than 0 for all X, but not equal to 0 vector because X is trivially equal to 0. Okay? Then A is called positive definite matrix. And there is a symbolism for this, A greater than 0. This is a notation, but please, I am not comparing anything. This is just a notation saying that this is true for all X not equal to 0 vector. Okay? This is called positive definite matrix. So how can I check this? This is the issue, but let's think about it later on. Now there is a second definition, very related. Well, this is an equality. Then A is called positive semi-definite matrix. Again, I am excluding the 0 case because 0 case always gives me 0, so I know that. This is called a positive semi. This is the word semi, and this is denoted by this. Okay. Again, equality denotes that, well, I have such an inequality for all X vectors except 0. So note, if minus A is, now I think it's clear, greater than 0, i.e. minus A is, so I'm multiplying by minus 1, positive definite, sorry, then this is called negative definite. And as you can imagine, it becomes a notation like this. If minus A is greater or equal to 0, I think it's clear, then A is negative semi-definite. And A is denoted by, this, negative semi-definite. Of course, this negative semi-definite definition is like trivial extension of this 1 and 2. So if I have a method for checking 1 or 2, I can always apply, I multiply this A matrix by minus 1 and apply the same method to decide whether, this another matrix is negative definite or not. So learning these two, how to check a matrix is positive definite or positive semi-definite, is sufficient. Because for the negative case, negative definite, negative semi-definite, you multiply this matrix by minus 1 and do the same check. Okay. Now, very good. I think we have understood at least what is the purpose of defining such a matrix. But let me write in our case, let me erase it further then. I want to keep this because now I want to show something else. So what was our A matrix in this example? It was 2, 4, 4, 2. Okay. Now, I won't be discussing this, but it's very easy to see. eigenvalue, lambda 1 of this is 6, and another lambda eigenvalue of this is -2, and eigenvalue corresponding to this, E1 is 1, 1, and E2 is 1 and -1. Let's say that I have calculated that. Can I check this? Multiply this A matrix by 1, 1 from right. So you get 6, 6. So eigenvalue is 6. Multiply this A matrix by 1 and -1. 2 minus 4 minus 2. 4 minus 2 is 2. So -2, 2. So if I multiply this by -2, so indeed, it's all correct. This is eigenvector with eigenvalue -2 and so on. Okay. Very good. Now let me think about the following. So if I have such a matrix, well, now this is my previous plot. Now I'm thinking about this optimal vector. Now there is this 1, 1 vector like this, and since they're orthogonal, there is this other vector 1 minus 1 vector. So how about this? Now I'm at this optimal point. Let me mark it. And I move by this direction along this eigenvector. So previously I can go right or left in the one-dimensional case. Now I can go in any directions. That is the reason, for example, this gradient is calculated and so on. So if I go in this direction, so what will be the value of the function? Is it increasing or decreasing? Of course, remember, after this moving to the origin, now I'm at this point, and so this is U transpose, a U function. So you may say that, okay, U transpose plus a constant. So a constant value. This is the constant that we have said JXX optimal. Okay. Now I am at this origin. This is my, let's say, U1 coordinate. This is my U2 coordinate. Okay. So I'm going in this direction. Later on I will go along this direction. So let me write this. J, U, U, U transpose. This is, maybe you will get confused, I will call this M. J transpose M U. So this M is, previously we have defined A as something else, A plus A transpose, which is this, okay? Now, over here I am fixing my U vector as 1, 1 times T. T is, the scaling factor. So this is 1, 1 and T. So what do I get? Since this is M times U is an eigenvector, so I get 1, 1 eigenvalue 6. So at the end I get the following. 6 T square, and that is it. So after this multiplication I have this, and actually let me have 12 T square. So if I multiply this by this vector, I get 6, 1, 1. I have 6T times 1, 1 after this. Then U transpose times 1, 1 is, I get 12T square. Okay. So if I go in the other direction, so I'm fixing this to 1, 1 and T. 1, 1. Yes. So what do I get? This time -2. So I get minus 4t square. Okay. I think we got the idea. Okay. So what do I see? I see that if I go along this direction, if I move along this direction, I see a function like this, 12t square. As I go along this direction, if I, for example, write these, if I, let's say, move my hand, so I get a value like this, increasing value. And similarly, it goes like that. Okay, a quadratic. So along this line, so it's increasing. And over this line, indeed, this is a minima. If you are fixing your domain to this line on this plane, then indeed origin is the minima. Because if you go in this direction, you get an increasing function. You go in the other direction, you get an increasing function, and so on. But how about the other case? In the other case, it's a decreasing function. So if you go this way, just the opposite. Now, if I deviate from this optimal point in this direction by t units, or here, by t units, now it goes inside of this whiteboard. So if I'm over here, it goes in, because this is a negative quantity. So what do I see is that now this optimal point is neither maxima or minima. So we see that XOPT is not a maxima or a minima of JX. Okay, so this is called, actually, there is a third case you can remember from calculus, saddle point. Okay, so it is a saddle point. If it's an extrema, which is not a maxima or minima, so it's a saddle point. But during this calculation, we have learned quite a lot. So assume that eigenvalues of this matrix is 6 and 6. Then in any direction that you move, you get an increase, at least in these two directions. Now if you move in a linear combination of these directions, since all of these quantities are positive, their cross product will be positive, and so on. Actual cross product will be equal to 0 because eigenvectors are orthogonal. Okay? So you get again a positive quantity. So what do I mean by that? So if I, for example, move by alpha E1 plus beta E2, this, now I have eigenvector 1, eigenvector 2 scaled by alpha and beta. What will be this function, if that will be the case? So I get the following. Now I have alpha E1 square plus beta E2 square. Okay? Let me explain. This is not exactly correct right now. Let me write one more time. So I have alpha square, E1 square, lambda 1, beta square, E2 square, lambda 2. I think right now it's correct. So what's going on? Now you have this M matrix. If you operate by this M matrix by something like this, again you have 4 terms. Okay. So one of the terms is E1, E1. E1, E1 term, because there is an eigenvector relation. So I get lambda 1 and norm of this vector. So similarly, among these 4 terms, I have E2, E2 term. It is this one. E2 norm square. And that is it. So I have E1, E2 term also, but since these eigenvectors are orthogonal, because of these properties of this, symmetric matrix, as we have said. So this is the reason that we are selecting like that. So we see that they are not appearing because that inner product is equal to 0. So clearly, if these eigenvalues are positive, this will be always positive. But in our case, one of the eigenvalues was negative. So we run into a trouble, and we have seen that if I go in that direction, in this direction, So this equality is not satisfied. Okay. So let me write this. If a matrix over here, sorry for this, is not satisfying any of these, not satisfying, let me say 3, 4, 1, 2, 3, and 4. We call this matrix an indefinite matrix. Indefinite. So it's neither positive nor positive semi-definite or negative definite or negative semi-definite. This is indefinite. And this corresponds to, in our case, an indefinite matrix. Okay. Well, very good. So let me write now some results. So results. Number 1, A matrix is positive definite if and only if this is all eigenvalues of A. So as I have said, we are considering symmetric matrices in general. Okay, symmetric matrices. If it's not symmetric, we can do something about it, but it's not the case. Let's focus on symmetric. In our case, we have symmetric matrix. All eigenvalues of A should be non-negative. That is, lambda k should be greater than 0 for all k. Since this is symmetric, these eigenvalues are real valued. It all makes sense. Number 2, so let me say, another way of checking positive semi-definiteness is checking leading principal minors of A. So let me write an example. So just a brief example. 1, 2, 3. Well, let me write 2, 4, 5. Something like that. I have a matrix, a symmetric matrix like this. So how do you check whether this is positive semi-definite or not? Well, you check this determinant. Okay, so this is the leading principal minor by deleting second, third rows and columns. If this is greater, this determinant is just 1, it is positive. Then you check, 2 by 2 determinant from this. This is the reason it's called leading. From this lower upper corner, 2 by 2 matrix. This determinant is equal to 0, so it does not satisfy this. If it satisfies, now you check this. Okay, let me change this then. 0.1, 0.1. So you check this determinant. First determinant is 1. The second determinant is 4 minus 0.01, 3.99, second determinant. The third determinant is this, calculation of this. So if, let me call this determinant 1, determinant 2, determinant 3 of these matrices. If all D1, D2, D3 are non-negative, then A is greater than 0. Okay. So this is positive definiteness check. If this matrix is bigger, if it's 5 by 5, you are checking D1, D2, D3, D4 and D5. You are making this calculation to cover this whole matrix. Okay. Now, almost done. But please remember, these are the methods to check positive definiteness. Definition of positive definiteness is, this is not the definition. Of course, this is equivalent to the definition, but the main definition is Now, practical definition, this is greater than or equal to 0 for all x not equal to 0. This is the definition. Sometimes students confuse the definition by this practice of checking positive definiteness. Of course, this implies the definition, so this can be the definition, but physically this does not carry any importance. But this quadratic form carries lots of importance. Okay, now almost done. One more comment and we will conclude this hour. 2. A is positive semi-definite if and only if I'm just all eigenvalues should be positive. This should be positive. Should be positive. Sorry for this mistake, but lucky that we have catched. So this is correct. They are all positive. D1 greater than 0. D2 greater than 0, D3 greater than 0. Okay, what is this? If all eigenvalues are non-negative, that is lambda k greater than or equal to 0, then we say that matrix is positive semi-definite. Checking leading principal minors is not sufficient. So we have to do more checks for deciding A greater than or equal to or not. Okay, I won't be discussing this. Please check, let's say, Wikipedia for A greater than or equal to 0. Okay, so I won't be telling this. I mean, you have to do more checks essentially. So please check this Wikipedia page for principal minors, positive definiteness checks, and so on. You will get this result. So as you can imagine, this is very important in many cases. Like in optimization, you are discussing a point is maxima or minima by looking at this matrix, A matrix, at the optimal point. And if this matrix is positive, let's say semi-definite, then you say that this is a minima. This corresponds to a minima. If this is a nonlinear function, then you calculate, a Taylor series expansion, a quadratic at that point. So this A matrix corresponds to, second derivatives of that nonlinear function. This can be second partial derivative with respect to x, second partial derivative with respect to y, and xy derivatives and so on. You calculate that A function, A matrix, and you check whether that A matrix is positive semi-definite for nonlinear functions and so on. So this is our extension of basic knowledge of calculus for single variables to multiple variables, as you see. So it's a very important result actually. Okay, well, good enough. We will discuss more things later on, and that will be it for today. Thank you very much.